Our first presentation this morning is going to be regarding cathodic protection testing. This is Lori Granelli. I'm sure most of you know who she is. And really, we probably don't need an introduction because most of us have dealt with her in the past.
There's a lot of new people.
But Lori Granelli is the Director of Technical Services for the Steel Tank Institute, STI, and Steel Plate Fabricators Association, and it has a BSME from Illinois Institute of Technology in Chicago, Illinois. STI SPFA consists of over 200 members who fabricate steel storage tanks for petroleum products, water and chemicals, steel pipes, and pressure vessels. Employed with STI since 1990, her current responsibilities include overseeing STI's technical standards, conducting research on issues such as alternate fuels, maintaining STI's UL listings, presentations, and education to industry, and overseeing STI's Cathodic Protection Tester certification course.
You don't have to read all this.
Yeah, it's just a repeat. I will tell you this. Lori has come to Wyoming 3 or 4 times over the last 10 years and has assisted our testers, our CP testers, because in Wyoming, we only accept certification by NACE or STI to get a CP tester's license. And I'll tell you, once we started requiring that in our state, the quality of testing has improved drastically. And if it wasn't for her and NACE, we would have a lot more failures, we think. So, anyways, Lori.
Thank you. Get this down to my level, okay. Whoop. All right, we're going to talk about cathodic protection testing today. So we're going to cover, this is all going to be really brief. When we do our certification course, it's a 1.5-day class plus a half a day of testing. So we're going to condense all this down to a little more than an hour. We're going to talk about galvanic systems and impressed current systems. We're going to talk just about the very basics of cathodic, what is cathodic protection, how many readings, where to take them, what does it all mean, trying to understand all those forms. And I know this is all of yours forms, but it's just to give you a quick background, what the forms are and where the information is supposed to be filled out. And a little bit of troubleshooting. You see something that doesn't look quite right. What does that mean? And we're going to talk about one of the big things, the newer things that we get questions on, new being a relative term, is about testing flex connectors. Because even on a fiberglass tank, if they have that flex connector in the dirt, which is something that's going to go away as all the secondary containment requirements come into place, but right now that happens at quite a few sites still, those flex connectors, if they're in the dirt, have to have cathodic protection. We're going to talk about the requirements for testing those. Okay, so first of all, what is cathodic protection? All that you're doing is taking 2 pieces of metal, 2 different types of metals, and you're connecting them. And what you see here is a chart that shows the relative energy, how much energy each of those pieces of metal have. You can see magnesium's all the way at the top. It has lots of energy. It likes to share all that energy with anything else that it's connected with. Zinc is next down on the line, and in the middle is steel. Further down is platinum and gold. So that means gold is really stable, and that's why you get a lot of jewelry, rings made out of gold, because it's really stable. If you have even a silver ring, it's going to tarnish. It can leave marks on you, and because as you can see, looking at this chart, silver's not quite as stable as gold is. That's all that this means. So what is a corrosion cell? I thought I took away all these goofy little things. Corrosion cell is made up of 4 components. You have an electrode, an anode, a cathode, and they all have to be electrically connected. They have to have a metallic path. And when you do all that, when you connect them together, you're going to get that flow of current. The energy flow is always in DC, direct current. Direct current just means that it's a flat line, unlike the voltage that's coming out of the walls, which is AC, which just means alternating current. So cathodic protection is always in DC, just like any battery. Good example of galvanic cathodic protection, not just because we happen to represent STIP3, but it is a very good example, the STIP3 tank. Now, you probably don't see too many of them looking this nice and pretty, but this is what they look like before they go in the ground. They do come in different kinds of colors or coatings. I get these questions a lot as people are trying to identify what that tank is that's in the ground. And depending on the size of the tank, they'll have 2, 4, 6, 8, 10, 12 anodes on them. Since, I'm not even sure how long, 1987 and maybe even before that, all the anodes are welded on, and that's the electrical connection. So that piece of magnesium or zinc doesn't do any good if it's not connected to the steel. So to make sure that installers were actually making that connection, we had the manufacturers weld on the anodes. It's much harder to disconnect if they're welded on. Not impossible, but it's much harder. Okay, so what is an STIP3 tank? P3 just stands for 3 forms of protection. It has electrical isolation. Because if anybody that's ever taken NACE, which is used to stand anyways for National Association of Corrosion Engineers, if you've ever taken their course, they always tell you that in order to use galvanic or sacrificial cathodic protection, you have to have your piece of metal isolated. And that's so that when you're doing those calculations to figure out how many anodes you need, you know exactly how much metal there is to protect. In order for cathodic protection, sacrificial protection to work well, it has to be very well coated. It's only going to work effectively if there's a minimal amount of metal to protect. And that's why you have that isolation again, so you know exactly how much, and then you're going to coat it so there's a minimum amount of exposed metal, exposed steel. And then the sacrificial anodes, the galvanic anodes, will be able to provide that power, that current to protect it. Okay, so that explains how a P3 tank works and how galvanic protection works. Having said all that, now you've got this bare steel tank in the ground. Hopefully not anymore, but say you did have some kind of bare steel in the ground. Why is it corroding? It doesn't have anything else connected to it. It's just a piece of steel. So what happens is in making steel, you put a lot of energy into it. You put all these different materials in it. It's all heated up, very high temperatures, and then that steel is going to be rolled flat. Now you've got your piece of steel at your manufacturing facility. They have to take it and they're going to roll it. They're going to weld it, and in doing that, they're putting lots of energy into that steel, into that tank. But the energy isn't going to be exactly distributed uniformly. So the steel kind of winds up looking like a puzzle piece. And there's different energy levels in each of those crystals. So the energy levels create their own galvanic cell. And the ones that have the highest, most negative energy level are the ones that are going to corrode quickest. So in this little puzzle piece here, the one that at negative 615 millivolts will become the anode, and it's going to sacrifice itself. It's going to corrode. And that's why you get that pinpoint corrosion, because it's going to all focus in one area. Okay, so that's the background of what corrosion and cathodic protection is. Now we're going to talk about how to test. Really simple. All you need is 3 things. You need to have a meter. Got to have something you're testing, so you're going to have some leads to connect to your structures, and you're going to have a reference cell. We always use a copper sulfate reference cell. So what you're doing is you've got your, kind of summarize this all up, your galvanic energy series with your metals at all these different energy levels. You've got your anode that's at the highest level. You have your steel that's at the in between. And you're connecting it up just like you would a battery and a flashlight. In fact, this is kind of fun if you have kids that are in grammar school and they need to do science projects. You can actually make a battery. So you can you can make a flashlight. So you make your own little battery with a piece of steel and a piece of magnesium, and you can make a little flashlight light up by just making this connection, putting it all in water. It's kind of fun. My daughter did this one year, and a long, long time ago, yeah. Okay. Like I said, that's all you're going to need for your testing equipment. Now, usually what we're going to use, when you're actually out in the field, because service station's pretty big, you're going to use reels of wire, not just little short sections of it, but that's all that you need. When you're looking at this reference cell, you can see it has a piece of copper in the middle. The copper sulfate are those blue crystals that are in there, and that's how it gets its name, copper sulfate. And you really do need a copper sulfate reference cell. Putting a piece of copper in the ground, trying to use that to take your readings does not work. But what it's doing is providing you a consistent basis. Because, you know, some areas of the country, you can put steel in, it's really not going to do very much. You have all sand, it's very dry, you don't get a lot of corrosion. Where some areas, you have corrosion happen very quickly. So by using this copper sulfate reference cell, you have a basis from which all the measurements are made. And that's why that negative 850 number makes sense, because you're always basing it off that copper sulfate reference cell. So as I said, we're always going to use DC volts. You want the tester to put this, if you're out in the field watching somebody, you want them to put it on the lowest setting possible. Because when they see negative 1.4, if they keep switching that dial down a little bit more, they can actually get a different number. So you want the lowest resolution on that meter that you can get. And by doing that, you're going to remove one of the sources of possible errors, and you're going to have the most precise measurements you can. Now, if it's reading negative 1.4 millivolts, and the magic number is negative 850 millivolts, there's really not too much of a concern. But if they're reading negative 855 millivolts, or 850.85 exactly, you really want to make sure they're as precise as possible, because you're getting close to kind of that, you know, break-even point, and you want to make sure that everything is in good working order. We tell all our testers that all the equipment should be calibrated at least once a year. Reference cells actually should be calibrated more often than that, and that depends on how often they're being used. Have they picked up any contamination? If they're out at a site that's heavily contaminated, that gasoline or fuel at the site can actually get soaked up through that porous tip. So when they're going to recalibrate, they want to use pure copper sulfate crystals. They want to use distilled water. Again, this is to eliminate any sources of error. And really important, because I've tried this a lot of times, it doesn't work unless you do this the night before. As Oma said, we go around and we teach these cathodic protection classes all around the country. We started using sealed reference cells after a couple of years, because what happened is these things were constantly draining all their water from being shipped around. And we'd get there in the morning, fill them up with water, and they didn't really work very well. So now we use sealed reference cells. So it is important that they be recharged at least the night before. So we tell all the testers the very first reading that they're going to take on a sacrificial system, if they're testing an STIP3 tank, is a remote reading. It's going to be at least 30 feet out, and we're going to talk a little bit more about that. But at least 30 feet out away from the tank. To use that as your first reading, it'll give you a very quick, good idea of how well that system is operating. I'm going to have lots of examples. As part of the recertification, we allow folks to recertify online. But because I'm not a particularly trusting person, I have them send in to me 3 sets of test reports that they've done recently being a relative term. I don't really care when they did them. They just have to send me in 3 test reports. And we've seen some really interesting things. Not all of these are from testers, thank God. They were certified by us. But they are examples of real test reports that have been sent in. So here's the first one, and I always love the anoid and Catholic protection. I mean, you can't make that kind of stuff up. So these are the actual readings that were sent in. So the first thing is the sheer numbers, negative 13.2. And for those of you that aren't math whizzes, negative 850 millivolts is 0.85 volts, a whole lot less than 13. The very highest potential, if you paid attention to that chart at all, if you happen to notice, I didn't really point it out, for magnesium is negative 1.7 volts. So to get negative 13, like, I don't know what you were testing, buddy, but I don't think it was the tank, really. That's the first thing. And then the second thing is he has 1 reading for his tank, 1 reading for his pipe. Not at all acceptable. Another point would be, what unit are these? Negative 13. I'm assuming that's volts, but if anyone, you don't want to make assumptions. A lot of bad things can happen once you start assuming. And the numbers simply don't make sense. And, this is a heck of a deal on some of these. So this is another one. You can see, he's trying to be fair in his pricing. But again, he's given 1 reading for his tank, 1 reading for his pipe. And you would think this kind of stuff has gone away. It has not. Okay. A lot of the pictures are going to be from our classes. I like to point out that these are examples of how regulators test tanks. You've got to do things as a group. That's a joke. Probably not a very good one. Okay, so where you're going to make your connection to the tank is critical. Most of the time, when they're connecting to the tank, what they're going to do is drop a stick down to the bottom with a nail and a piece of wire around it. It's the easiest way to do it if they don't have anything fancy. The testers that do this all the time have come up with some pretty creative, good ways of making electrical connections with equipment that can be put together and reused very, very fast and cleaned up, because they're going to be putting this in their vehicle and they're dropping this down into a tank holding petroleum product, so getting it cleaned up in a reasonable way is always a good idea. But how they make that connection to the tank really doesn't matter, so long as they have a good, solid electrical connection. You're trying to measure something that's less than 1 volt. It's a very small amount. You've got 110 volts coming out of your wall. That's not even going to kill you. So 1 volt is a very small number. You need to be as precise as possible. You have to have a good electrical connection. Where we place that reference cell is everything. Every time that reference cell is moved, the number is going to change. And I've seen lots of results where people have moved their connection to the tank instead of moving their reference cell and given 3 different numbers. And again, I'm kind of shaking my head like, how did you do that? But that is why we stress that so much. It shouldn't make any difference. Once you have a solid connection, it's all continuous. It's a piece of steel. So if you connect to one end of it or you connect to the other end of it, it's all electrically continuous. The number should be exactly the same. You can tell we really emphasize that point. We say it a lot. Okay, and I know you can't see these things, so I'm giving you kind of an overall view of parts of reports that we've gotten, and then I'll give you a close-up of it here in a second. So this was 2 tanks. We have a diesel tank and an unleaded tank. This is a form. A lot of the states, how many of you have forms that are either suggested or required in your state? Yeah, quite a few. Yeah, we're seeing it more and more. I think it's a great idea. It's much easier for you to analyze it and see, did they do everything that they should have done? So they've written down where they made their contact. They've written down what structure they were testing. They put down where their reference cell was located and what their local reading was and what their remote reading was. Okay. Now here's a good example. What they've done here is they did move the reference cell. They've got it in the 4-inch manhole, their probe manhole, under the diesel pump. But they've also moved their connection to the tank each and every single time. So they have it down through the spare 4-inch riser, down through the probe riser. Why? There's absolutely no reason. That somebody doesn't understand what they're doing or why they're doing it. But they did give us a site drawing, so that's always good. Okay. Because the measurement that you're taking is very small, another way to minimize the error is to always make sure that the reference cell is placed in moist soil or backfill. So if you have someone that's concerned about a new inspector that's concerned, they see a tester out there and they're pouring water on the site and they're concerned about something funny going on, perfectly normal, perfectly acceptable. It's actually something that we encourage. It improves the repeatability of the readings by minimizing the resistance that reference cell is seeing right at that tip. And that's really all that it's doing. You're not doing a whole lot there. It's just minimizing the amount of contact resistance that the reference cell is seeing. What you do want to do is to avoid placing that reference cell where the soil is really dry, where there's contaminated soil, which I know is really difficult to get around, but that reference cell will soak up the fuel. You want to keep it out of frost or frozen soils because the resistance is going to be extremely high. Current doesn't want to flow through that. You want to keep it away from grass or any other vegetation. You absolutely do not ever want to see that reference cell on concrete, on asphalt, on anything other than soil or backfill materials. Plastic-lined flower beds. Now the big one for that is some of these truck stops are really big. They go for quite a long ways, but every once in a while you'll see a little bit of green. And the problem with that is where that green is, it could very well just be a little plastic liner of soil. So when you place that reference cell in this plastic liner, it's like putting it in a sump. And that reference cell can't really see the tank or other structures because it's isolated from it. Which is another reason for taking multiple readings, not just using one reading. Because you can get one reading pretty much to say anything you'd like it to say. So this is pretty much the procedure that we give all the testers. Tell them turn on their meters, to turn it to the lowest setting possible. Take the cap off the reference cell. It's always fun in the exams watching people trying to take their readings in their little tubs with the reference cell cap on. Just kind of shake your head like, buddy, this isn't going to work. They have to consistently use the same connections, and by making their connections like this, black to the reference cell, red to the structure, they will always see a negative number on that meter. Not such a big deal for a galvanic system, but for impressed current systems, it's a really big deal because it's very easy to, I don't know about easy, but it's not that difficult to switch up those leads when they're being connected together upon installation, and you could have some really bad things happening and the tank getting corroded very quickly. So looking at and making sure that number is negative and always making those connections the same way is really critical. So then we want them to verify that they are in true remote earth, not just place that reference cell down 30 feet and say, okay, I've got this, but verify that that is true remote earth. And the way they're going to do that is by moving that reference cell 10 feet. They're going to look at the number that they get, and they're going to verify that it's within 10 millivolts of the same reading. And by doing that, they know they're in true remote earth, and they can use that as a valid number. They're going to record everything on their site map. They're going to show where their tanks are. I don't care if it's not a very pretty picture. It really doesn't matter. They want little X's or some way to indicate where the reference cell was placed, so that when you're looking at the numbers on your form, you can then look at the site drawing and actually see what they did. As a tester, I'd want to do this just to kind of cover my butt, if nothing else. So in case anything ever went wrong, I'd have as much information as possible. If they need to, because they cannot place that reference cell on concrete, they want to drill holes through that concrete. They have little pencil reference cells they're really pretty small. They're the size of a pencil. That's why they get that name. And they can go right through that concrete. The difficulty is going to be that once you drill that hole, it's going to be extremely dry in that area. And so water is going to have to be added, in particular in those instances, to try to get any kind of number that makes sense. Okay, I really like these things. And yeah, I am kind of a geek. I look at it. It's the kind of stuff that I think is fun. So they submitted their form. They've got their description of what's at their site. They've got a site map. Again, it doesn't have to be real pretty. They did continuity testing. They did their CP test. Okay. So for the continuity readings, they show a fixed cell reading for their tank, and I'll explain a little bit more about what that is. But to start with, what they're doing is taking a remote reading on the tank at some distance away. So that's their remote reading. Now they've got their local readings on their tank in another location. So their local readings are negative 914, negative 865, negative 855. But their remote reading is negative 671. Should this tank pass or fail? Oh, come on, you guess. It's 50-50 chance. Huh? What? Bueller? Yeah. What do you think? Pass? Fail. Fail is correct. Now, I don't have any prizes, so that'd be cool, but I do not. The way STIs, we do have a test procedure. In fact, I have a few copies. If anybody would like a printed copy, you're more than welcome to it. But if you're like me, you don't want to carry stuff around. It's also available up on our website, and if you give me a business card or send me an email, I'll be happy to email it to you free of charge. So according to STI's recommended practice, all the readings have to pass. The remote readings must pass. The local readings must pass. If they don't pass, the system fails. Now, it doesn't mean that they can't have somebody with higher credentials, a NACE CP expert or a NACE certified person come out and say that everything's okay. There could be a valid reason. But as a tester, with the credentials of a tester and the experience of a tester, they would have to fail this system. Okay. So how did all this stuff come to be? Why is it that we're taking a lot of, well, not as many, but there are still some states that really want to see those 3 local readings over the tank? STI's recommended practice was just redone. In fact, this is dated April 2017. I think we actually finished it up last year, but things were a little busy in our office, so it just got published this year. There was a lot of debate about this, even within our own committee. So our committee consisted of tank manufacturers, because STI is a trade association consisting of tank manufacturers, but also we had a group of testers, of NACE CP specialists, and then we had a group of tank owners. So we tried to get a balanced committee, and this was very highly debated. Every time we talk about it, it is. And the STI's recommended practice does say you have to take 3 readings per tank. You have to take at least 1 local and at least 1 remote reading. The way that it came up, at least from what we know about it, looking back at records, and why 3 readings would be taken is in the old days, tanks were smaller. So they might be 24 feet long. If you look at what a reference cell is actually seeing, it's only seeing kind of like a flashlight. It's only really seeing that distance directly over the tank. So if the tank had been buried 2 feet and the diameter is 8 feet and the tank is 24 feet long, by placing the reference cell in 3 spots, you're seeing directly over the top of the tank, the entire tank. Kind of makes sense. But where is that tank going to corrode? If it's going to corrode, I kind of like to think it won't if it's a P3 tank, but you know. If it were going to corrode, it's going to corrode on the bottom. So this reference cell, by taking those readings only on the top of the tank, is not seeing any possible corrosion on the bottom. Or it may not. It could totally miss that. Keep wanting to touch the screen. I have a computer with a touch screen. Kevin Henderson, who used to be with the state of Mississippi, so back in the days when he did work for the state of Mississippi DEQ, STI went to him because we had heard he was going to write a book, like the first CP testing manual, how to do it. NACE had been talking about doing this for years and could never really get it out and done the way that Kevin wanted it done. Very simple, very, this is what you must do. So we went to him to talk to him about doing remote readings on tanks. He was not going for it. He did not really believe us, to say the least. It's like, kind of like, well, you guys are industry scum and you're going to say whatever works for you. And, Kevin's not like a super smiley, outgoing person, and he and I are very good friends now, but at the time, he was not exactly giving us a warm and welcome. So we gave him our spiel, we did our class, and then he went out in the field and had all his inspectors actually try this. So they took lots and lots of readings. And what they found was that in cases like this, you're in this STP, and these are real sites down in Mississippi. At least they were at the time. I probably haven't changed all that much. I don't know. Every time you move that reference cell a little bit, the numbers changed. So here you are within one containment, and you're getting all these different readings. Does this really mean that the readings over that tank are changing that much in this small space? Or are the readings being affected by the metal that's in that sump? And again, we were measuring a really small number, and by placing that reference cell close to other metals, there is a direct effect. And this is what Kevin was finding out, that these readings are affected by things other than the actual true reading on the tank. So they did this in lots of other places. And you can see, depending which number you took at this in ATG, your tank is either going to pass or fail. So as a tester, which number do you use? You want to do the right thing. You don't want to pass something that shouldn't pass, but you don't want to fail it either if it doesn't need to fail. A customer's going to have to do something, and if they dig up this tank and everything's perfectly fine, they're not going to be very happy about it. So then they tried taking these remote readings. And they placed the reference cell way out there, took a bunch of readings, and they found that those readings actually were more representative of the actual tank. The readings were very consistent. They didn't always pass, they didn't always fail, but for the most part, they were very consistent. And you can think about that remote reading as representing the entire tank. Because again, if you're looking at it like a flashlight, it's going to see very focused for the short part, but it's also going to see, I speak like I'm Italian, for a very long distance. It's going to see further out for quite a long ways. So the farther away you put it, the more you're going to see of that one structure. And what we like is it helps to mitigate all those environmental factors that are directly over that tank. All the metal piping, all the electrical connections. A tank is very different from a pipeline, cross-country pipeline, which is what the majority of NACE corrosion engineers are testing. So it has all this equipment directly over it. And by using this remote reading, you're able to mitigate some of those factors, to eliminate that from the readings. One of the big things, even more so now, are anodes that might be dropped 2 feet down for whatever reason. A steel pipeline that they just suddenly realize they have. And so they think it's a good idea to drop that anode right there at the structure, which is never a good idea. But that anode is going to have a big effect. And we show this, we demonstrate this in our classroom. We have little tubs that we bring, and again, this is our idea of fun. And if you put that reference cell right there next to that anode, and if you're ever out in the field and you want to try it, there's an anode out there, put the reference cell right next to it, take a measurement, put it 20 feet away somewhere where you don't think there's any metal, take a measurement. I can guarantee you that number away from that anode is going to be lower. That reference cell has a huge effect. Same thing if you have a fence around the perimeter, and it's a galvanized fence, and you put your reference cell right up next to that galvanized fence, it's going to affect the numbers. That's why some of the testers like to have one reading, because you can get that number to say anything you want. Our one instructor says that a lot. He says, well, I'm an honest person, but if I weren't, and I could take one reading, I could go to that tank owner and say, okay, what do you want it to say? Do you want this system to pass, or do you want this system to fail? I can make it do either one. Just tell me what you want, if all I need is one number. So pea gravel and crushed stone are difficult to get readings through because they're very dry. They're very good for corrosion protection because they drain very well. So without that water around the system, the metal's going to last for a long time. But to get your readings, they're very dry, and it helps to have moist because that's how you're going to get current flowing. The old thing about don't stand in a puddle in a lightning storm, right? Because that current's going to flow right through. So again, a real example of things that happen directly right over the tank at this particular site. All these local readings failed. We had negative 525 at one end, negative 590 at the other end, negative 435 right in the center. The remote reading is negative 940. We happen to know this is a very dry area. They've had a very dry season. They have pea gravel as their backfill material, all really good for structural support of the tank, all great for not making that tank corrode. But taking these readings, it's not a good combination. So our tester, having a little bit of knowledge about how this all works, is saying, well, it's just the pea gravel over this tank. That's what's causing that reading. And he's probably right. Okay, here's another question. Pass or fail? How many say pass? How many say fail? Fail it is. All the readings have to pass. And again, if they want to pay the money to have somebody with higher credentials, they can do that. They can do some additional testing. The first thing they would do is to do soil resistivity measurement and see how wet or dry that backfill material is. They could do a current requirement test and see that this tank really isn't taking a whole lot of power to bring it up to a protected level directly over that tank. So there's other things that a corrosion engineer could do to actually measure this, not just come out there and do some kind of, ritual, everything's good, bless this site, a little more than that. Okay, so we talked about how to establish remote earth. This is what they're going to do. They start out at a certain distance, and we use 30 feet just because it's some reasonable distance away from the tank. There's really nothing magical about it. Sometimes you do have to go quite some ways, and yes, if you're in the city, this can be really challenging. We have had wires going across streets in the past, and people looking at us, and we've had folks, that whole thing up here yesterday with, Heather coming up and, hey, what you doing? We get a lot of that. People get concerned because they, see wires, and they, in the city of Chicago, they start thinking about bombs, and it's like, no, really, we're okay. You know, try to wear a safety vest, look professional. Sometimes you do have to go some distance away, and sometimes it can be difficult, and sometimes you just have to say, this is the best we can do. But in the perfect world, you're always going to take a remote reading, you're always going to take a local reading. One of the big questions I'm asked a lot is, how far is too far? So this is Kevin Henderson's slide, but I really liked it, so I just used his. Like, there's really no too far away to be remote. It doesn't make any difference. You just have to be remote, and you go until you get that stable number. Okay. There's typically for a galvanic system, we're going to be using on readings, and an on reading just means that that cathodic protection is on. It's not turned off. On an impressed current system, that's really easy to do. You go and you flip the switch, the system's off. On a galvanic system, particularly an STI P3, where the anodes are welded to the tank, you're not going to disconnect anything. I mean, it's on. It's on all the time. And so we've taken a lot of readings, and we've proven that using those on readings is acceptable. Where they've added supplemental anodes, what the tester should be doing is adding them in a test box where the anodes can be disconnected. And in doing that, they can get an instant off reading. And an instant off is where you just temporarily turn the system off. It's going to be the second number that pops up on their meter. That's what they call the instant off. I know it's a lot of terminology, but you know what? They're not acronyms anyway, so that's one positive. But we do spell this all out in our test method, and we do have short procedures written out as well. Anyone that would like to have any of that, just let me know, and I'll get that out to you. So they're going to do one of two things. So for the readings where they can't disconnect the anodes, they're going to do their on readings. If they're supplemental anodes that they've added to it, hopefully they've done it the correct way and they can disconnect it and take those instant off readings. They'll get more accurate numbers. Any metal product, you guys know this better than I do, I'm sure. Anything that routinely contains product that's metal has to be cathodically protected or corrosion protected somehow. So flex connectors that are stainless steel, metal product piping. Don't see as much metal product piping, but it's still out there. And hopefully what you want to do is to place that reference cell away from the anodes. And again, when you're in a contained area, that can be really difficult. So the first thing that the testers have to think about is, again, where they're making that connection. So they're trying to connect to piping that's underneath the dispenser, or they're trying to connect to a flex connector that's underneath that dispenser. Well, that dispenser is going to have isolating bushings in there. So they need to get underneath that isolating bushing and connect to the actual structure. And that alone can be a challenge to do that. And what we would like to see is if they're not in a contained area, otherwise, they probably aren't going to need flex connectors, although, as I said, sometimes there is soil or backfill material in some of these contained areas. So for these flex connectors, we want to see two readings, one in the area, in the local area, and if you're within 12 inches of that anode, it sure as heck better pass. I mean, there's really a problem if it's not going to pass if it's right there. And we'd also like to see a remote reading, so that reference cell placed further away. And that's, again, because where you're placing that reference cell is right next to that anode. So we want to see the local and the remote. If they can't do that, again, this is in an ideal world, hopefully they've connected that anode in a way where it can be disconnected. And then we'd like to see those instant off readings done. And that will really give the best measurement of how much cathodic protection is on that structure. Now, Now, if it's in a sump like this, and they've got an anode on there just because they can't keep the water out of it, they're only going to be able to take a local reading because that structure is going to prevent them from taking the remote readings. It'd be like, having a bucket and setting it above ground. It really doesn't do you any good to try to do a remote reading. It's all going to be shielded. If you have to place your reference cell in a bucket like this, you don't want to completely submerge it. So where that connection is, that little copper tip on the end, make sure that stays out of water. So if you're doing this yourself or if you're watching a tester, all good points to remember. Piping, the rule of thumb is you want to test at both ends of the piping. So they're going to typically test at the submersible pump, and they're going to test underneath the dispenser. Test both ends. Now, if they do have piping with cathodic protection, and the installer did things correctly, they probably have their anodes at both ends. So it's more than likely to pass, although by now the system's probably pretty old, so you never know. But that's the rule of thumb. If the piping run is more than 100 feet long, they should be taking a reading in the center. So they may have to drill through some concrete to get that next reading. Okay. So you're an inspector. You get out to this site, and you're looking around. You're trying to figure out what do they have going on. Now, first of all, this is a pretty nice site. I like to be able to get out to sites like this all the time. You have some nice mountains in the background. This is from a class that we were asked to do in Alaska. And if anybody's here from Alaska, we would be happy to go back again. Just saying. Hawaii's another place. Happy to go. So you're looking around, you're trying to figure out what's going on. There's not a whole lot there. You see a couple of dispensers. You see some cracks in the paving there. You can see the manways, but what kind of cathodic protection does it have? And as I'm trying to explain this to tank owners, I mean, go inside and you want to look for a box, right? Look for a rectifier. Well, then the first thing they do is they find their Vita road. Oh yeah, we've got impressed current. No, you don't. Nice try, but. So we tell them to look for something that reads volts and reads amps. That would be a rectifier. Sometimes they're inside the store. Most of the time they're inside the store, but not always. Especially in warmer climates, you might find these outside. Let me go back. Up in the right-hand corner, this system has an anode junction box. That's what that is up on the top right. So all the anodes are wired up into a separate box. The advantage of having something like this is that you can test each of those anodes separately. So if one anode goes out, you can test it and know that there's no power going to that anode, which is really nice for a troubleshooting thing for the tester and for the corrosion engineer when that system starts to fail. Because these things aren't going to last forever. We've seen these in all kinds of locations, and when we get to, we go to an impressed current system and a galvanic system for every class. And this is a picture from a class, and I walk in this room and see it up there, and I'm like, oh my goodness, how are we going to do this? So we had to get a ladder and have every person in the class go up there and make all the connections. It was not a whole lot of fun. And then look at that electrical connection. They've got an electric wire going across over the doorway, down the side. I mean, is that up to code? I really doubt it. But that's a different problem. Okay, so you're out the site. You're going to look for saw lines, cut lines in the concrete. If you can see lines that look like this, if you can see those arrows, they're very straight, going across, going at another angle, going across. You can have a pretty good indication that they have an impressed current system. Not always. They could have added some supplemental anodes to that site, but it's highly likely that that's an impressed current system. The rectifier should have all this information on it. It's going to have a data plate telling you who made it. on-off switch, you're going to have the AC input, you're going to have a coarse and a fine. Our testers are not certified to change any of those settings. That it's a different course, different learning requirements to do that. They may be, but not through us. So the first thing we want them to do is to test the output voltage. And this is information you should look for on those forms. If they're testing impressed current system, they have other options. They're always going to have, they should be measuring their on readings, their instant off readings, and if those don't pass, the instant off readings don't pass, then they're going to be looking for a 100 millivolt shift. So here's some of the terminology that we're talking about. We have a native potential, static potentials, polarized potentials. The polarized potential is what we really want to see, because we want to know how much current, how much power is on that structure. They need to take at least 3 readings on every structure that's connected to that impressed current system, the tanks, the pipes, anything else that might be connected. They need to establish continuity between all those structures. They need to know that everything is absolutely connected to that rectifier. Because if it's not, whatever's not connected, but within that sphere of influence of that impressed current system, is going to corrode. That's just the way, it's just what's going to happen. There'll be a stray current effect happening, and it is going to corrode more quickly. So everything that's in the ground that's metal needs to be connected into that impressed current system, if it's within that sphere of influence. The testers are going to look at the hour meters. As an inspector, it's one of the quickest, easiest things to do. Has that system been left on? Has it been running the entire time? Because if they're turning it on and off, and it takes like the power of a light bulb to keep these things running, very little power, there's absolutely no reason to be turning it off. Look to see if there's any broken wires. Just look for the obvious things. The testers are going to measure the output voltage, the output current, and they're going to be doing the instant off readings. If they go out and they test all around that tank and the piping, all their instant off readings are more negative than negative 850 millivolts, they've done their continuity testing, everything's continuous, they're done. They're good. The reason we want to use the instant off reading is excuse me. Again, we're minimizing errors. The big mistake we see testers doing are using the on potential measurements. I'm going to go through some of this a little bit quickly because I'm going to run out of time. 30 minutes? Okay. So this is the big picture slide. This is the one that I really like if you are at all interested in how this works. So with an impressed current system, what you're seeing across that horizontal line, that's with the rectifier turned on. And you've got a great reading, negative 950 millivolts. That's awesome. We only need 850, so negative 950. You go out there and test with your impressed current system on, and everything looks great. Okay? Unfortunately, that number means nothing. Absolutely nothing. The reading on has a lot of error in it. It just doesn't mean anything. So what the tester's going to do is they're going to turn the rectifier off. And when we say off, I don't mean off. It's more like interrupting the power. So you turn it off very briefly, turn it back on. A lot of testers, if they're testing impressed current systems routinely, have a piece of equipment that's called an interrupter. And it will cycle it on something like 2 seconds off, 12 seconds on. So a very short off and a very long on. And the reason they want that type of cycle is so they don't mess this up too much, so that they keep the system energized. You want to keep those potential levels at the same number. because you're going to be they're going to be out there potentially for quite a while taking measurements. They're going to have to keep moving their reference cell to different locations, cycling this on and off. And so the advantage of having an interrupter is they're not running back and forth to a rectifier. They can just have it cycling on and off, and they can just be outside where the tanks are, moving the reference cell, getting all their data. So getting back to our chart, they've got this on number. What you see in the vertical line is what's called a voltage drop. In this case, their instant off read negative 700 millivolts. So the voltage drop, or otherwise known if you're familiar with the NACE term, an IR drop, is simply an error in the measurement. Doesn't really mean anything. It's just an error. So when you hear about this magical IR drop, it's just an error. It doesn't mean anything. It doesn't matter if anybody knows what that number is. What really is important is that instant off reading, negative 700. So you're thinking, well, that's a long way from 850 millivolts. How can that system possibly be protected? You've only got negative 700 millivolts of protection on that system. Well, the thing about it is, if you go back to that first chart and you look at all the numbers, there's a range for steel. So steel in the ground, according to that chart, can read anywhere from negative 500 millivolts to negative 700 millivolts. And that's a pretty big range. And in actuality, I've seen steel in the ground read as low as negative 400 millivolts. It really depends on what the conditions are at that site, what the native soil reads. So, they pick negative 850 because they want to be conservative. That's what engineers do. We want to be conservative. You got to have a safety factor. You got to have, you got to know for sure, 100%. It's like building a bridge, right? You don't want it to fall down. You want to be absolutely certain nothing's going to fail. So there is a very large safety factor built in there. In reality, all that you need is 100 millivolts of power on that system. So if your tank started at negative 400 millivolts, if that was the native potential, sometimes we call it the static potential, if that's what it was without any cathodic protection on it at negative 400, it would only have to read negative 500 millivolts in order to be protected, to be fully protected. And the first amount of cathodic protection on it does the most good. Now, it's not to say that if it's at negative 400 as their native and they get negative 450, that it's adequate. I'm not saying that. I'm just saying that it does have some protection on it. Don't turn it off. It's not at a level that it can pass, but it is still doing some good. So that negative 850 number, you have to use it for on systems because there's no way to get these instant offs. But it's probably higher than it needs to be. Can't really be sure. So for these impressed current systems, the tester's going to do their instant off readings. If that doesn't pass, what they're going to have to do is go back, find the exact same spot that they placed that reference cell, because every time they move that reference cell out in that field, that number changes. And they're going to do what's known as static potentials. Now the static potential is just that. Static means constant, not changing. So the static potential is what that number is after the system's off and it's not changing anymore. In reality, we don't really care. If it's at, say your system's reading like this, negative 700 millivolts. In this case, that static potential is negative 575. As soon as that number drops below 600, as a tester, I'm turning it back on. I'm done. I've got 100 millivolts. I don't really care what the static number is. I want a passing number. I want to know, is this system protected? I'm getting paid by the hour. I'm out of there. And that's perfectly fine. This is the one formula that we give people in our class. We don't really expect anybody to memorize it. But voltage is equal to the I, which is current, times resistance. And it's just a kind of an easy way to remember it. Voltage is at the top, I times R. If you can remember what all those things stand for, you've got it. V is kind of simple, voltage. I for current, I have no idea. It's just what it is. And R is the resistance. And the resistance is how much force, how much push does it take to get that current through the soil. So the drier the soil is, the more push, the harder it is going to be to push that current through the soil. And because there's so much more current, so much more power in an impressed current system, that's why that IR drop is so much more significant on an impressed current system that's got at most 1.7 volts, 1700 millivolts. It doesn't have a lot of current to push through. So there's much, because there's a much smaller I, there's a much smaller IR drop. And it's not typically very significant. Okay, another form. You just never know what I'm going to get when I see these things. It's like, okay, this could either take me 1 minute to review this and they're good, or otherwise I'm sitting here looking at this for a while trying to figure out what did they do. Okay, so this site here, this is really nice. They've got a really pretty site map. I always like to see this. They've got their form. Looks like it's pretty well filled out. Okay. This is an impressed current system. They should tell me that they've got 3 tanks. I should have zapped out all the site results. I just realized I'm showing all that. Oh well. And I tried to circle the areas that are important. So my circles moved a little bit in translation here. But what's over on the far left is the rectifier on. So those are their on readings. Negative 0.862 volts, negative 0.648. Those are the first two numbers. Okay, then they turn the rectifier off. I'm assuming those are just instant off readings. Kind of hard. Well, actually, it does say native. That's their native readings. Negative 274 millivolts. Like, wow, that's low. Even, you just don't often see something that low. Negative 294 millivolts. It's like, again, that's really low. So if you look in their remarks, they say, hey, this system passed. It meets the negative 850 and it meets the 100 millivolts because they're looking at the difference in their on and the off. So what does that on reading tell us? Nothing. It's a trick question. Absolutely nothing. The on reading tells you nothing. So when I see this, they fail. They do not pass go. They do not collect $200. Okay. Let's see. What did they do here? I'm trying to remember. What did they do? Oh, I see what they did. Okay. So they've got their tank. This is an impressed current system. They've got their on readings, negative 1250, negative 1294, negative 1311. They've got their instant off readings. Instant off is more than negative 850. System passes. Anybody see anything funky? I don't know if you can actually see it. It's fairly large. So look at where they've placed their reference cell. So that's the first thing. They've got it at a riser. Well, I mean, maybe that's one. That's okay. Maybe it's not. I don't really know. Made their contact at the bottom of the tank, the bottom of the STP. It's like, okay. But then when I realized, it's like, oh, there's 3 tanks. They only have 1 reading for every structure. When I first looked at this, I'm thinking, oh, they've got 3 readings. No, they've got 1 reading. So it could be that they've actually placed this reference cell in an appropriate place. I don't know what the bottom of the STP, how you possibly make a contact with your tank like that, but the fact that they've only taken 1 reading on every tank is not acceptable, particularly on an impressed current system. When you look at where those cut lines, if anyone's ever paid attention, you'll see that those anodes go completely around the tank. And any time an anode goes out, you're not going to have protection in that spot. So it's really critical that you take measurements around the entire system. You could never pass a system with one reading. Okay, so that's the formula that they're using. They're taking the instant off, and their static readings, it has to be more than 100 millivolts. Okay, same kind of thing. They're saying they're I mean, some of these are just too funny. You got your tank to soil reading using your reference cell. This one, if you look up at their site map, they've got 4 structures here. It's like, I don't even know what you're trying to show me. I mean, is this supposed to be, I really don't even know, but they've taken their native information, they've taken their on reading, so the first thing is they're looking at their on and their instant off, and that's not going to work. If you go back to that formula that you have to take the instant off and subtract that from your native or your static potentials. So that's just not going to work. And again, if they have other tanks at the site, they have to be connected in. I don't see this as often, but I still do get this question from people. If they happen to have anything else at the site that has metal in it, even if it's a natural gas pipeline going through it, that impressed current system is going to be affected. If you're out at the site and you're walking around, look for wires coming through those cracks. You can see the saw cut lines. If there's wires coming through, the system might be working now, but if those wires are cut, it's not going to be working. You know, the 4 elements of cathodic protection, you have to have a metallic path. You cut through a wire, you no longer have a metallic path. Okay. This site here, we have 1 diesel tank. It's 4,000 gallons, steel tank, steel piping, no flex connectors. Gave me a nice drawing. Everything's all nice and square. Like, okay, I can see that. I've got my numbers here. Here's the reading for the diesel tank on top. The second line is for the line, the diesel line. They're showing where they've contacted it. This is what a lot of these state forms look like. So the location code, sometimes I'm a little confused on where everything is wanted, but generally you have what the structure is, where did you connect to it, where did you place your reference cell, what's your on reading, what's your instant off, and if you use the 100 millivolt shift, what those numbers are. And then at the bottom, at the very last thing, always important, did it pass, did it fail? You need a very clear statement. And again, they've taken 1 reading for the tank, 1 reading for the line. And believe it or not, I got this report in last week. This was from a person that went through our class. And needless to say, he has to go retake the class. And I will say, if you find a tester, an STI certified tester, that is not testing in what you think is an ethical manner, they are not following the rules, please let me know. We will revoke their license. We will start out by telling them very clearly that that is not acceptable and that it's not allowed. And if they don't see the error of their ways, we will revoke their license. Okay, so continuity testing is required for impressed current systems. STI P3 tanks are designed to be electrically isolated. Most of the time, they're going to have these nylon bushings. So if they're retrofitting a P3 tank for some reason to an impressed current system, they should be connecting in those any of the lines above, fill lines, in my opinion. I mean, technically they don't have to. It's not routinely holding product. But if they don't, that pipe is going to corrode. So they have 2 methods of testing continuity. One's called fixed cell moving ground. And a fixed cell moving ground is simply taking remote readings on any and all structures that you'd like to check to see if they're continuous. If those readings are the same, the structure is continuous. If they're 10 millivolts or more apart, they're isolated. So as an example, you've got 3 tanks. You've taken remote readings on all of them. One's negative 725, one's negative 724, one's negative 910. The first 2 are only 1 millivolt apart. That's definitely less than 10. Even if you're not a math whiz, that's less than 10. And so those two structures are continuous, but structure B is isolated from structure C, as well as A being isolated from C. So that's fairly straightforward. The downside to using fixed cell moving ground is it's time sensitive. It's hard to gather up the data quickly enough to make those numbers consistent. So we really prefer using this point-to-point method. To use a point-to-point method, all you're doing is simply connecting to the two structures. Connect to one structure, connect to the other structure. No reference cell, that's it. One end of your meter is to your tank, the other end of your meter is to your fill pipe, for example. Those are two very easy things to connect to. If those numbers are greater than 10 millivolts apart, and you'll know because you don't even have to do any math, you're just looking at your meter. If it's more than 10 millivolts, they're isolated. Now for an impulse current system, that would be bad. If it's a P3 tank, that would be good. If they're doing this at a rectifier, the rectifier should be turned off. Again, that's to minimize errors. And we recommend testing for continuity between everything. Kind of points that should be done, always take it about the same time of the year. That's really not so much a problem. Now that 3-year deadline, people take that very seriously. And they have to meet that, so that's pretty much always a given. Flex connectors. These particular flex connectors, they've only taken local readings. They took the readings on, so they only have one reading. Now you think, okay, maybe that's the best they could do. They get out to the site, and that's how they found it. But no, they also sent me the bill for where they charged the customer to install the anodes. And I'm thinking, well, that was kind of stupid, folks. I mean, you know, you're looking for my blessing on the system. Why didn't you just hook it up the right way? Hook it up so you could take an instant off. And then they could have taken their readings so they could see that negative 850 instant off and really know that they've done something to protect those flex connectors. All of the forms have a place to do a site drawing. That's pretty much a given. So what happens if the system doesn't pass? Well, according to federal regulations, they have to have a CP expert do a design. The other document that STI has is a recommended practice for the addition of supplemental anodes. We had a CP expert sign off on it so that that could be used instead of, so that for those P3 tanks that don't meet the requirements, it's an easy fix, very conservative, but easier than having to hire an expert for every site. For an impress current system, maybe they can simply adjust the rectifier. That's really between the owner and the CP person. We give out free documents to any state people, so if you'd like a copy of this, just let me know. Again, our main purpose was to try to make things easier for the tank owners that needed some help, give them an option to hiring a CP specialist. Get a little plug in here for Cromco. Where's Ed? You owe me, Ed. I use that slide a lot. And this is the scope, what it covers. It doesn't cover anything to do with impressed current systems. It won't handle soils that are extremely dry, only up to 40,000 ohm centimeters. They have to do a current requirement test, so there's limits on how much current it can take. Again, it's a very basic, very conservative approach. And then we give some drawings to show where the anode should be placed. Critical thing to note is anodes should be placed below the level of the structure. And this is true for anything. Pipelines, flex connectors, it should be placed below the level of the structure. And that's all that I have. I want to save a little bit of time for questions. Hopefully I have. Yeah? Okay. Yeah? Okay, great. Questions? If no one has questions, you get lots of extra time, but okay. You can start since you've got it.
So, Laurie, if a system has been off for some time,
yeah,
how long is good enough to turn it back on? Let's say 6 months, a year, somebody's shut power completely off. Stations boarded up.
So this isn't about whether or not the system is really functioning. It's about whether or not the tank has corroded. That is a tough call. It's probably going to be a case-by-case basis. I would look to see what condition or what's the age of the tanks to begin with. But the problem is, how do you evaluate it? There's really no good method out there other than doing a tank tightness test, which is just going to be a point in time to say that those tanks are okay. So obviously that's something that should be done. But there's no real accurate way to determine the corrosion rate in that 6 months' time. But 6 months is probably fine, in my opinion. But you're getting longer than that. Yeah, it's like, why? Why would you do that? Given all the regulations nowadays, I just don't think that's a good idea. Besides, our members would like to sell them a new tank, so. Yeah.
He stole one of my question, but I have a second question. When a system does need to be repaired, I'm getting some pushback from an owner, so I'd like some clarification. They keep going out there 3 times now and have proved that the system is failing, but they haven't actually yet repaired it. Is there an amount of time between the repair and the last test to help determine the design or the repair on that system?
I'm not sure I understand what you mean. Like, when should they actually do the repairs?
Yeah, does a test need to be done right before the repair to help with the design?
No.
I guess that's my question.
So if they're going to do a repair, is the repair on an impressed current system or on an impressed current system? It kind of depends on how they have it set up. So if they have an anode junction box and they can measure each anode, it probably would be helpful to have that right then, because then you know how much power each anode is able to produce. So if one anode is totally unfunctioning, then clearly they need to go and replace that. On the other hand, they could simply have a whole bunch of anodes in their truck, test it on site while they're there to do the repair, and do it like that. I mean, if that were the case. So I don't, at some point you just do it, right? I mean,
yeah.
I would say that's not they're just kind of spinning their wheels and trying to.
So there's no need to do the test, it doesn't sound like, right before the repair. Like I said, they keep going back out there. Okay.
No, I mean, sometimes designs are done a long time before the installation's actually done, and initially nobody certainly wants to go back out and retest the site.
So it's not based on the current conditions, it's based...
Yeah, well,
okay.
At some point in time, you take the conditions you have, and that's it.
Yeah.
And you make sure it's working, and you make modifications if you need to.
Okay, thank you.
Yeah. Yeah.
Yeah, Lori, really appreciate STI's leadership through the years on this whole subject. You all have done a really great job. My question is more practical, I guess, than technical, though. It appears that over time, the demand for competent CP testers and CP engineers is probably decreasing out there in the real world, and we also know that petroleum equipment companies are having a really tough time hiring and retaining quality people. You come in contact with a lot of these folks in your classes, so you probably know better than I do what the real world out there looks like. I guess my question is, do you foresee a problem in some states with retaining competent people to do this work over the next 5 or 10 or 15 years, or not? Do you think that's going to be an issue?
I am continually amazed at how many people sign up for these classes and the level of demand. STIP3 is a wonderful tank, but because of the regulatory requirements, who's going to buy a new tank that has to be tested every 3 years? I mean, most of the time that's not going to be their tank of choice. Occasionally, So the majority of STIP3 tanks in the ground are much older. And even with that, we put on at least 6 classes a year. Our classes are limited in size to 24, but we fill up these classes all the time. Occasionally, right before class, we have somebody call and say, hey, our tester just quit, we need to send somebody else. I've only gotten pushback from 1 or 2 companies, though, about having a problem keeping testers. So I am surprised at that. I would have the same opinion as you. I don't know that that's actually happening. And if anything, I think because the certification goes with them, those testers then go on to other jobs. So it might be hard for the companies paying for the class. And I do agree with Oma. I think it's really important to have people that are trained doing this. I wish it were something, we say it's really super simple, and it is, but just doing those basics, having a little bit of knowledge is really critical for something like this.
Measuring half a cup isn't hard either, but my husband can't do it, so yeah.
Over here? Okay, thanks.
Did I hear you correctly saying that the continuity value should pass like the test value also?
For impressed current systems.
For impressed current?
Yeah. STI is not, we do not push the requirement for continuity testing for STIP3 tanks. I realize that a lot of states do, and that's certainly your prerogative. You guys are the ones holding the big club, so go for it if that's what you want. In my opinion, it's not that important for a P3 tank, because if the tank is continuous with any amount of extra metal, it won't pass. And it just won't. So it's going to come up. I don't see the need to do that continuity testing for P3 tanks.
The reason I'm asking you about that, because in all our past training, they said the continuity number doesn't matter as long as either continuous or isolated, but is above 800 or below 800, it doesn't matter. So is that
for STIP3 tanks? That's true, but for an impressed current system, the reason it makes a big difference is if everything is not connected to that rectifier, you're going to get stray current on it. So let's say you've got a flex connector on top of that tank, and they've decided they're going to protect that flex connector with just a simple galvanic anode. Well, clearly, if you think about how that current is all flowing around through the ground, it's within that line of influence of that rectifier and all that power. So what happens is the current comes along through the ground, all nice and fat and happy. It jumps onto the tank like it's supposed to, and then it sees that flex connector, and it thinks, oh, that's an easier path. Current, like everything else in nature, including your children, including your spouses, is lazy, right? It's going to take the path of least resistance. And if it can jump on that flex connector with less energy than it to keep moving along that tank, it's going to do that. And that's fine. Where it jumps on is great. It's given that nice power. But where it jumps off is the problem. So when the current leaves, that's when corrosion is going to start to happen. So if it's not continuous with it, something is going to corrode that's not intended to. That's the reason for it.
Thank you.
One quick question. Great presentation, Lori.
Okay.
Just a couple quick questions. One in which, how does a high water table affect cathodic protection readings? We've got tanks that are completely submerged in groundwater with about 4 feet below grade, where the anodes are actually submerged. Does that affect, or would it affect any of the test readings?
Oh yeah, anodes love that. They do. It makes it really easy for the current to flow. The resistance is extremely low. Your anodes might get used up a little bit faster because they're going to put out more current, but the system should work great in high water conditions.
Okay, and one more quick question. Earlier on, you showed some slides of some test results where they had individual tank readings and individual pipe readings, and you said they weren't supposed to test them individually, so I'm assuming...
No, you are supposed to test them individually. They didn't have enough readings in those cases.
Okay.
So you need, in an impressed current system, you need 3 readings per structure. So 3 readings on the tank, 3 readings on the piping, 3 readings on everything is just kind of a good rule of thumb. For a sacrificial system, piping is generally tested at both ends of the pipe run, so 2 tests.
Okay, and then lastly, and this is for you and for the audience, do you think a failed CP reading is reportable as a suspected release? Because
No.
we're trying to determine whether we should actually require folks to report, and does other states require reporting to their agency if you have a failed reading?
Well, you might want to have them report a failed reading, but it is not. Just because the cathodic protection system isn't working is no indication that the tank is not tight, not related any way, shape, or form. I mean, you think about how long some of those old steel tanks were in the ground. Some of them were 50 years and they came out looking fine. So you've got a steel that's a quarter of an inch thick. Now the CP isn't working. It's going to take a long time before a hole develops. Not to say they should leave it that way, just to reinforce that they're not connected to a leaking tank and one bad test. It's going to take a while. Now, one thing I forgot to mention is on those impressed current systems, if you ever see positive numbers at an impressed current system, have them shut it off. I said the first amount of cathodic protection does the most good, so always leave it on. But if they go out there and those numbers are reversed, what that means is that tank is being used as an anode, and it could cause that tank to fail very quickly. So if they have positive numbers, have them shut it off. The one and only time we shut off a system when we were out doing a class was we found the leads reversed. Anything else? I'll be around through tomorrow. Anybody else has questions? Great way to reach me is by email. I do travel quite a bit. Our watchdog program is still alive and well. If anybody has questions on that, not my favorite part of my job, but it's certainly part of what I do. Or anything else, I've been with STI for 27 years, so I know a little bit about a lot of things, and happy to talk to you. Thank you.